In this presentation, I will continue where I left in the previous video. So here I will discuss about hybrid tooling approach. So as I mentioned, our tool should serve dual function of a, let's say, multi-mode waveguide for the laser, as well as it should have sufficient conductive area to serve as an ECM tool. So here we can see the tool is designed with an outer concentric layer of stainless steel and an inner concentric layer of quartz glass. So here we use quartz glass so as to separate, let's say, the internal reflective surface of the tool from corrosion with the contact of the electrolyte. And we can also increase the acceptance angle of light into this tool electrode by means of this quartz glass. So here we can see on the left we have an optical image, and on the right side we have SEM micrograph of the developed tool. So since this wall of the metallic electrode is not a perfect reflector, so we get, let's say, combination of diffuse and specular reflection. So it's not a perfect waveguide, so leaky modes propagate inside the tool. So we can see also here, this is a schematic of how we determine the efficiency of our hybrid tool. That is how much power output we are getting in relation to the power applied into a controller. So we can see here that if we have a new tool on the first day, we can get as high as above 40% of the power which is applied to the controller. And then, let's say, over the time period, it can drop, let's say, up to less than 20%, because the internal, let's say, there's solid deposition inside the tool electrode and we lose the power. And of course, this power is a function of, let's say, tool length as well. So as we increase the tool length, the power output decreases, because, let's say, we lose some fraction of power in every reflection, and longer the tool, we will have more number of reflections. So this is on the right hand side, we can see the simulated, let's say, intensity distributions at the outside cross section of the tool. So the intensity distribution resembles more like a multi-mode waveguide, where in the center we have higher intensity modes, and on the, let's say, periphery or close towards the internal edge of the glass capillary, we have, let's say, low intensity modes. And it's good to see that most of the intensity distribution is inside the, let's say, glass capillary from where the electrolyte exists, and there is basically a very little intensity or negligible intensity over the cross section of the glass. And on the bottom we can see, let's say, a spot diagram, which is basically simulating the path of the rays at the cross section on the outlet of the tool. So we can see that most of the rays from the RMS value as well exist from the internal diameter of the tool electrode, that is, they exist through the electrolyte, and very less are exiting through the, let's say, glass capillary. So the laser power is not only determined from our tool, and it's not also determined from what we give into a controller. It's also a function of the flow rate which we use for the electrolyte in our system. So it's a compromise between, let's say, what flow rates are good for flushing for the ECM process, as well as for the alignment of our laser. So we can see that at low flow rates, let's say up to 32 ml per minute, the laser is perfectly aligned, because the electrolyte is a perfectly cylindrical shape and it's very well transparent, so the laser can propagate over long distances, and the alignment is very good. But as we increase the flow rates, we can see that the Reynolds number approach more towards the turbulent regime, and the electrolyte behaves like a spray, and we lose the alignment. Also, if the flow rates are higher, we get more let's say, convection cooling, and then the laser heat is not getting into the workpiece surface in proportion to what we applied, so the power efficiency is not that good. So in the framework of Microman project, we also do some inline metrology on our machine. So we have, let's say, a Hall current sensor to monitor the process current. We also have, let's say, temperature measurement devices on the machine to measure or record the temperatures close to the machining zone. And we also put high-speed camera close to our machine to see what is exactly happening in the gap when laser is hybridized with ECM. So we know in ECM we have hydrogen bubble generation and gas evolution, but when we put laser, these rates are expected to increase. So we are going to study this with high-speed camera-based observations. So these are some of the initial experiments we did on hybrid laser ECM in the framework of Microman project. So on the left-hand side, we can see an experiment of a point removal on Inconel IN 718 material without tool rotation. So we can see on the outer periphery we have electrolytic flow effects, and in the center is laser localized ECM zone. And on the top right hand side, we can see, let's say, this is not a perfectly aligned process where we can see some scattering at the tool electrode, but this is a perfectly perfectly arranged or aligned process. And the bottom two are the cavities, which were machine wide laser ECM. So in the center, we can see that we have laser localized process zones. I will discuss this in the part 3 of the video.